Here we are, together again, taking a look at a new topic: torque power measurement. As we've seen previously, the torque and power of a compression ignition engine is developed thanks to a glow plug, which, when heated, increases the temperature in the combustion chamber and generates self-combustion of air and fuel. These two parameters mainly depend on the correct calculation of the air and the RPMs at which the crankshaft rotates. In particular, all injection strategies include calculation of the engine load or the incoming airflow, more or less accurately starting from measurements made by one or more sensors connected to the ECU and using more or less complex formulas. Measurement of the number of revolutions per minute, also known as RPMs. This information is used to understand the operating point of the engine. Commonly, vehicle manufacturers communicate the curves of torque and engine power measured in the condition of maximum performance. Often, this condition does not correspond to the situation in which the engine uses the maximum amount of air, but rather when the position of the accelerator pedal corresponds to 100%, especially for engines controlled by an electronic control unit. The engine torque curve for the fully depressed accelerator pedal is marked by 4 points: minimum motor torque, maximum motor torque, also called peak torque or nominal maximum, engine torque at maximum power, engine torque at maximum RPMs. Diesel engine has the peak of maximum torque at low engine revolutions, and the number of revolutions that can be reached is much lower compared to a petrol engine. The maximum power curve with the accelerator pedal at maximum is characterized by 4 points: minimum motor power at maximum torque, maximum motor power, also called peak power or nominal maximum, engine power at maximum RPMs. By observing the horizontal axis of the engine revolutions, which serves to describe and compare the torque and power curves at full load, 4 points can also be identified in this case: minimum engine revolutions at maximum torque, engine revolutions at maximum power, maximum engine revolutions. Let us pause to analyze the last 4 parameters. Let's start by saying that the minimum engine RPMs does not refer to the engine idle, which for a diesel-powered road vehicle ranges approximately from 750 to 850 RPMs, depending on the engine coolant temperature and atmospheric pressure. The minimum engine revolutions refers only to the engine speed from which the vehicle manufacturer has chosen to start the test. The engine revolutions at the maximum of torque are precisely those corresponding to the maximum of the torque curve. If the engine control in question has an injection strategy based on torque, it is very likely that one of the maps marked with the words maximum torque limiter or maximum torque contains the same value expressed in Newton meters declared by the manufacturer, or a value very close to it near the engine RPM value at maximum torque represented on the axis of the map itself. The engine revolutions at maximum power are those which correspond to the maximum of the power curve. Currently, there are no engine control units based on power calculation, but some manufacturers have already begun to include maximum power limitation maps within the calibration files. The current control units based on engine torque are able to understand if the maximum power limitation value is exceeded through the modification of the original file, simply because the torque and the power are linked by a mathematical formula, as shown, which expresses the maximum engine power, in which we can identify the angular speed of the motor shaft expressed in radians per second, corresponding to the peak power which can be replaced with the speed of revolutions per minute. Remembering, however, to transform minutes into seconds divided by 60 and the radians into circumference, thus multiplying by 2 pi, and the maximum motor torque. By inverting the factors, we can derive the torque from the power. The maximum engine revolutions, rather, refer to the limiting speed normally stored indirectly in the ECU calibration file, depending on torque required at high engine RPMs, torque limiters, amount of fuel injected at high engine RPMs. The portion of the graph between minimum engine revolutions and the rotation speed corresponding to the maximum motor torque is called the lower band or the low band. The higher the full load torque value included in this area, the better the vehicle acceleration will be. When the engine works within the low range, if for any reason the friction forces were to increase, the engine RPMs would decrease, causing a decrease in engine torque and a consequent stall condition. The area between the engine speed of the maximum torque and the maximum power is called the high performance band or intermediate band for obvious reasons. Considering the situation in which, during a phase of extreme acceleration, when engaging a higher gear than the one currently selected, it would be advisable to do so when the engine revolutions are approximately those at maximum power. In this way, the decrease in RPMs caused by the transmission ratio of the higher gear would cause the engine to work around the maximum torque speed. Remembering that the maximum torque is physically linked to the maximum acceleration capacity of a vehicle, the situation described represents the optimal operation. In addition, specific fuel consumption is usually as low as possible in this RPM range. Let's analyze a consumption chart. The extreme acceleration phase does not represent the actual driving condition of a vehicle, but only describes the most favorable gear shifting condition. Today, manufacturers plan to equip vehicles with manual or automatic gearboxes with a number of gears ranging from a minimum of 5 to a maximum of 10, where the transmission ratio allows you to shift up to a slightly higher RPM at the maximum of torque without drastically reducing the RPMs or, in any case, remaining close to the border between the low and intermediate ranges. Finally, the range between engine RPMs at maximum power and maximum engine RPMs is called the upper or high range. The greater the full load engine torque in this band, the greater the horsepower. As the maximum torque is physically linked to the maximum acceleration capacity of a vehicle, the maximum power of the engine is linked to the maximum speed that can be reached by that vehicle, not counting the friction, of course. When the engine works within the high range, if for any reason the friction forces were to increase, the engine RPMs would decrease, causing a decrease in the engine torque. But in any case, it would drop in the intermediate range without unstable conditions. With this information, we can now understand why the performance of an engine equipped on a vehicle is measured in different phases, ways, and purposes, such as performance measurement during engine design, development, testing, and calibration, performance measurement on engine test bench, performance measurement on vehicle test bench, performance measurement through data acquired from the OBD2 diagnostic socket. Let's take a look at some of them. We know that inside the cylinders, the pistons collect energy during the expansion phase, and that part of the heat generated by the combustion of the air-fuel mixture is converted into mechanical energy. The gases that press on each piston generate a force that is transmitted from the connecting rod to the crankshaft, causing it to rotate. Energy, or work, is the product of a pressure for a volume. In our case, we are dealing with the actual average pressure acting on the piston, while the volume obviously corresponds to the displacement. The torque, on the other hand, is therefore the product of the displacement by the mean effective pressure. Of course, this is a fictitious pressure, which serves as a reference and to perform engine design calculations. The real pressure, instead, undergoes some variations depending on some operating conditions. The average effective pressure is generally defined as the theoretical average pressure that, if it were to act on the piston during the entire expansion stroke, would make the engine deliver the same power that it actually produces at that given rotation speed. The average effective pressure, expressed in bars, depends only on the product of the three yields: thermal, volumetric, and mechanical. It seems a useless value in itself, but we think that, after having designed the engine and developed the prototype with real dimensions,
it is unthinkable to start it without having performed the control calculations, with the risk of irreparably damaging it. This is, therefore, an extremely important and very useful parameter because it allows you to make comparisons between very different engines, even in terms of displacement, to know the degree of utilization of each of them and to evaluate the stresses involved. When we talk about the average effective pressure, we always refer to the pressure calculated at the maximum power regime. It is evident that between two motors of equal displacement, operating at the same rotation speed, the one with a higher average effective pressure provides a higher power. The power delivered by the engine depends exclusively on the product between the pressure and the RPMs, and that's why the average effective pressure is of fundamental importance for the purposes of performance. Instead, we define the average effective pressure indicated as the pressure calculated using the power indicated by the manufacturer. It represents the theoretical calculation of the power or work of the engine in converting the gas pressure in the expansion phase inside the cylinder in total absence of friction, inertia forces, and power losses necessary to move the auxiliary components connected by the belts to the crankshaft. At the end of the prototyping phase, the power or braking torque of the engine is determined, thanks to the dynamometers that can measure these forces directly on the engine shaft. This data is used to finally determine the average effective braking pressure. Thanks to the difference between the indicated average pressure and the actual braking average pressure, results in the average effective friction pressure, which represents the totality of the losses. This information is used by the manufacturer to know how well the design department has worked, to put into practice the considerations and objectives chosen at the beginning of the project. After the real control phase, the manufacturer proceeds with calibrating the ECU maps to determine one or more preliminary versions of the original file, which differ in maximum performance, sometimes changing some mechanical parts and sensors, while other times the motor configuration is identical for different nominal powers. During the calibration, the manufacturer carries out part of the measurements using an engine test bench, and when the vehicle prototype is ready, finishes the original mapping by measuring the performance on a test bench. The values of the maximum braking power and torque are to be considered the extreme objectives of any tuner who intends to develop the performance of the original vehicle, calibrated by the manufacturer to have reduced torque and power so as not to affect the reliability of the engine. Performance measurement on the engine test bench measures the maximum performance of the crankshaft before installing it inside the bonnet of a vehicle, connecting it to a gearbox and the wheels, thus completing the kinematic chain, and lastly, testing the final performance. This is usually done by the vehicle manufacturer or racing team. The performance measurements studied are those of the average braking effective pressure, therefore braking motor power and motor torque. Performance is to be considered maximum because the brake applied is the maximum possible. In addition to performance, specific fuel consumption is also studied in this phase. An engine test bench consists of a device that can apply a resistant torque to the shaft of the engine being tested. The resistant torque is variable and is controlled by integrated software. The brakes are of various types: mechanical, hydraulic, or electric with eddy currents. Thanks to this instrument, it is possible to measure several elements, such as the load cell, which is an electronic component capable of measuring a longitudinal force applied to an object, or the torque flange, which is a component capable of measuring a rotational force applied to a shaft. The engine test benches can be inertial or braked. In both cases, the motor is placed on an adjustable slide, positioned near a fan that can cool it and keep it at a constant temperature during the test, and then switched on. Then the software that controls the equipment will slow down the engine revolutions to the minimum sustainable by the engine, and then adjust the throttle to 100% in the shortest possible time. This will cause the RPMs to increase to the limit, normally controlled by the ECU. This operation is called a launch. The equipment of this type can also be used to refine the first calibration versions of the original files of the engine control units, because they can keep the engine revolutions constant and vary the accelerator, keeping the engine braked. They can also do the opposite operation, that is, allow the RPMs to develop to their full extent, keeping the accelerator constant. Considering that the accelerator controls the throttle valve more or less directly, individually varying revolutions and load, tuners who calibrate the maps of the original file will have to be able to adjust the main maps of the ECU that directly control the torque and power, respecting the emissions maximum allowed by the standard. Through an adequate calibration, for example, the engine manufacturer can create lower power versions based on the sales strategies associated with the vehicles in which it is installed. Conversely, a racing team can achieve calibrations that allow the engine to work as close as possible to maximum performance. When, however, we talk about performance measurement through vehicle test benches, the vehicle has already been produced by the manufacturer, and we want to test its final performance. Or perhaps, someone who owns a device of this type intends to measure the vehicle's performance throughout the tuning process, before, during, and after. Equipment of this type is divided into two categories: roller benches and equipment for measuring performance at the wheel or at the hub. The first type are the most common, but also the most expensive. Furthermore, it is necessary to receive adequate training or have a certain specific skills to be able to use them to minimize any measurement errors or situations that are potentially dangerous for people or vehicles. The second type, on the other hand, has been developed more recently because it is able to take extremely precise measurements without too many precautions and does not require particular technical knowledge. Both the roller benches and the equipment for measuring the performance at the wheel or hub can measure torque and power at the wheel, and depending on the brand and model, trace them back to the performance of the engine through the estimation of losses due to various sources of friction. Let's take a look at how the roller bench works. The vehicle is positioned directly above the bench, with the drive wheels overlaying the rollers that will take the measurement. Thanks to indirect calculations, the software of these benches can calculate and display the losses due to friction on the torque and power graph itself. In addition, the more accurate benches also have a device capable of measuring air temperature, pressure, and humidity, very important environmental parameters for the concept of test replicability. Benches can be divided into inertial and braking. The former are the simplest to make and are very precise, but they are only able to measure performance as a function of the vehicle's inertia. The latter are more technologically complex and can apply a braking load that operates as a real force opposing the traction force, measuring the performance of a vehicle with a braked bench that allows you to select the specific value in newtons that the brake must exercise is certainly much more precise, but much more expensive. The equipment for measuring performance at the wheel or on the hub, on the other hand, works with very similar physical principles, but by not using a roller, it allows removal of just a few sources of friction and makes the measurement less complicated from the point of view of the formulas to be considered. For the measurements at the hub, the vehicle must be perfectly balanced longitudinally and laterally to cancel the friction forces caused by the gradient due to the slope. But since the vehicle is mechanically fixed to the measuring instrument, this makes it the safest method from the point of view of the operator who must use it. Unfortunately, it is also the equipment that takes the most time to use. For measurements directly on the vehicle wheel, no special experience is required other than basic training. The equipment allows you to test the real performance of the vehicle on the road, which makes it among the most faithful equipment. But to be as precise as the previous equipment, it needs an excellent driver who replicates the same series of operations during different tests. The big difference is in the number of sensors and the speed and computing capacity of the electronic modules. Some of the previously described instruments have an OBD2 device capable of acquiring some values from the diagnostic socket that allow a significantly increased number of measurements to be made, or allow them to be associated with engine operating parameters.
Last, but important for all tuners, is the instrumentation used to calculate performance through the acquisition of values, measured by sensors or calculated by the control unit, and then made available through the diagnostic communication interface. It should be remembered that the accuracy, quantity and speed with which the data are acquired by the diagnostic socket strongly depend on the vehicle production year, the protocol used by the ECU manufacturer, the type of diagnosis accessible by the OBD2 device used. Without going into specific cases related to individual diesel car manufacturers, we can say with absolute certainty that all vehicles built from the mid-2000s onwards can provide a series of data generated by the engine control unit through the diagnostic interface. More precisely, we are talking about shaft rotation speed or the engine speed, expressed in RPMs, vehicle speed, expressed in kilometers per hour, or miles per hour, depending on the measurement system, international metric or British imperial, motor load used, expressed in load as a percentage value or dimensionless value, accelerator position, expressed as a percentage value. The engine revolutions will be used for the calculation of the power, the vehicle speed for the calculation of the acceleration, and to determine the aerodynamic friction. The engine load and the accelerator position are used to understand if the test is carried out at full load, and, therefore, whether the maximum performance of the vehicle is being analyzed or not. Any drops on the torque or power curve represent the reference for understanding whether the carburation adjusted during the tuning procedure is the optimal level or not. The protocol used by the ECU manufacturer and the type of diagnosis supported are two very closely related factors. For the sake of completeness, we will say that currently, for cars, the fastest communication protocol used by vehicle manufacturers is ISO 15765, which uses the standard CAN bus serial communication. While all vehicles and the control units that have controlled engines since 2002 have a set of data that can be acquired by OBD2 and basic diagnostic functions, which make up the PIDs, onboard diagnostics parameter IDs, thanks to the latter, it is possible to access the data necessary for the previously indicated calculations, albeit in a limited manner. The vehicle manufacturer also integrates its own diagnostic functions and data into the ECU, which normally provides the above values in a different and more precise way, but only for proprietary diagnostic instruments. Also, you need to get some information about the vehicle. Some of this is simple to recover, such as calculating the complete radius of the wheel, from the center of the hub to the outer surface of the tire, or knowing the mass of the vehicle when empty, found in the vehicle registration document. Others are objectively complicated to recover, such as the rolling friction coefficient between tire and asphalt, which can be considered the same for all road tires as a first approximation. The aerodynamic friction coefficient, the density of the air, which varies according to atmospheric pressure and its temperature, the front area of the vehicle in question. In any case, this information can be quickly retrieved from the technical specification sites on the web, so that it can be used to calculate less complex formulas. The physical principle behind this strategy is Newton's second law, also known as the principle of proportionality or the principle of conservation of momentum. During the test performed with this type of instrumentation, it must be remembered that the movement or motion of the vehicle driven along a road that is not a private race circuit is also noticeably influenced by the characteristics of the vehicle itself, not only the physical properties, but also the state of maintenance of the vehicle, the skills and behavior of the driver, the famous human factor, the characteristics of the road, presence of holes, puddles, gravel, etc., atmospheric conditions, heat, cold, rain, etc., the interaction with other vehicles or obstacles along the test course. Through the data acquisition from the OBD2 diagnostic socket, it is possible to obtain many other values that may help the computer understand if the mapping performed has altered the optimal control of the engine while having significantly increased its torque and power. We mention a few. The engine coolant temperature, or ECT, expressed in degrees Celsius or Fahrenheit. The exhaust gas temperature, also expressed in degrees Celsius or Fahrenheit. The current carburation, expressed in lambda or air-fuel ratio. Quantity of fuel injected, expressed in milligrams per stroke or cubic millimeters per engine cycle. The flow of air passing through the intake duct, expressed in kilograms per hour or pounds per hour. The air pressure present in the intake manifold, expressed in kilopascals. Rail pressure or pounds per square inch. The boost pressure generated by the turbocharger or compressor, expressed in kilopascals. Rail pressure or pounds per square inch. Injection time used as a function of engine RPMs and injected fuel, expressed in degrees before the piston reaches top dead center. Injection time used according to the injection pressure and the fuel injected, expressed in milliseconds or microseconds. The fuel injection pressure, expressed in kilopascals. Rail pressure or pounds per square inch. The indicated engine torque, expressed in Newton meters or pounds per foot. For the sake of completeness, it must be said that there is a category of instruments that take care of acquiring the previously listed data in real time, and others that are useful for tuning and more, called data loggers. The latter, however, were not included in the previous list since, by definition, they do not provide for measuring the performance of the engine or vehicle, but are still very useful in order to perform an excellent mapping.
Regardless of the methodology used to obtain torque and power, it should be remembered that the main purpose of a tuner is to compare the vehicle's behavior before and after the engine ECU remapping process. For this reason, and due to the high costs of available equipment, a tuner is normally able to have access to instruments that can be connected to the OBD2 diagnostic socket, or can use a vehicle test bench. If the first type of instrumentation has costs ranging from a few tens of euros to a few thousand, the second is much more expensive. The order of cost is about 1,000 times higher than the first case, from a few tens of thousands to hundreds of thousands of euros. For this reason, some companies or specialized tuning centers that own such equipment offer the possibility of making torque and power measurements as a service that can be purchased individually.
We have come to the conclusion. In summary, we have seen the measurement of torque and power through the illustration of the torque and engine power curves measured in the condition of maximum performance. Then, we went on to see measurement of the performance of an engine equipped on a vehicle through different stages, including performance measurement on engine test bench, performance measurement on vehicle test bench, performance measurement through the data acquired from the OBD2 diagnostic socket. See you at the next video.